Good morning. I'm Manoj Kumar Srivastava from the Department of Computer Science and Engineering, and today I will be taking lecture on data structure, and it is a continued lecture of tree data structure. And today's topic is binary search tree. The textbook which is to be followed here is Introduction to Data Structure in C by Ashok and Kamthe, Data Structures and Algorithm by Aho, Hopcroft and Ullman. These two are the best book which is to be followed here for the topic. And as the syllabus content is all about the C programming, that's why we will follow these two books preferably. And as a reference book, we can follow Tannenbaum, Data Structure using C and C++, and Sedgwick, Algorithm in C++. The topic is course outline out of his tree topic, and we will be starting here tree. The topic is binary search tree. Binary tree. Recursive definition of the binary tree is, as a tree we can see here, tree is a nonlinear data structure, and most of the tree programs are of recursive nature because we are really using most of the functions that will help you to perform the different operations in the binary search tree. An empty tree is a binary tree. A node with two child subtree is a binary tree. Only what you get from 1 by a finite number of the application of 2 is a binary tree. Here I have already shown that this is a binary tree. Now, binary search tree data structure that can support dynamic set of operations. And what are the dynamic set of operations that will be supported here is binary searching, minimum and maximum finding from the search tree, finding the predecessor, finding the successor, and insertion and deletion in the binary search tree. These are the operations that will be performed in binary search tree. This binary search tree data structure can be used to build dictionaries and priority queues. It is the application. These two are the application of a binary search tree, where most of the time binary search tree is used. Basic operation takes time proportional to the tree is big O of h, as it depends upon the height. Binary search tree, in this, what are the representation or what are the terminology that we are going to use here is root, key, left child, right child, and header pointer or a P, pointer to the parent. Now, as per definition, the property of the binary search tree is, whenever we are using binary search tree, as we can see in the diagram, that this binary search tree, if you consider the property here, it holds two child, that is left child and right child, or we can say it has two child. Here we can see here that this one is the subtree and this is the left subtree and right subtree. And in binary search tree or any search tree, there is left subtree and right subtree. The property is defined here based on this subtree itself. And if we go through the property, that for every y in left subtree of x, what we have to do here is we have to check that key y is always less than key of x. What here we are referring here is, if this is the root and the left subtree of the left subchild of this tree root node is 26 and the right child is 200. That means if you are considering as per the definition as property given here, for every x, for every y in the left subtree, for every y in the left subtree of x, this is the x, and key of y is always less than key of x, or key of x means from the root we can compare or from the right side we can compare. Since we have to compare this left child, it will always compared with the root child. So this will be always. In case of binary search tree, this will be less. And in case of right side, for every y in the right subtree of x, the 200 will be always greater than the x, that is key x or root x, we can say. So this is the property is followed for each subtree at each level. Means if you are considering at the different level, and this one is the third level. So for every level, if you are considering the parent here 18, the left child is lesser, the right child is higher or greater. This is what we have to look here, and this is the property that is to be remembered for the case of binary search tree. Now, in case of binary search tree, we have to perform the different operations, and one of the operation is traversal or traversing the tree, binary search tree. Here, in case of binary search tree, we are using the property. So binary search tree, we are using the property allows the keys of a binary search tree to be printed in monotonically increasing order recursively. As we have already know that the recursive property is very important for a nonlinear data structure. In case of data structure that is tree, we are mostly using the recursive nature of the pseudocode or program or algorithm that is to be followed here. So in order to traverse a tree, that is binary search tree, in order traversal, so what exactly we will do here, this is a pseudocode, that is we are going to understand what exactly it is saying. If x is not nil, that means we have to always check that binary search tree is not nil. Nil means what? If there is no tree or there is no root, then it is not possible to traverse there. Only we can traverse if there is tree with its left subtree and right subtree. This is what exactly this line explains. That if x is not nil, then we can continue the next step. What is the next step? We have to traverse in order tree walk. In order tree walk means what? We have to consider the, as per the property of in order, that is left node, and then we have to print the key, and then again we will call the in order tree walk for the right, and that is what is done in the case of in order. And here if we consider this tree in case of in order, what will happen here is this is the left node, this is the right node, and this is the root node. In order traversal is the, in case of binary search tree, it is a mirror image. If we consider here in this tree, this subtree, we can see here that in order traversal is always the mirror image of the whatever data is present in the different subtree, and while traversing in order, it will give the data as a 12, 18, 24, next will be 26, 27, 28, now 56, 190, 200 and 213. This means what? Whenever we will traverse the in order in a tree, we will get the output as a ascending order of the tree, that is each element will be printed here in ascending order. That means the traversing process of in order walk will be left node, root and right node. This is to be followed here, and this is what this recursive definition, this recursive pseudocode helps you to traverse and print the values of the tree, binary search tree. This is a tree. This is a tree. We will get here mirror image. If we walk in this pattern, since root node is considered here, this is not a nil, and left subtree we have to walk the left. If it is not nil, then we have to walk left. We have to then print the key. Since again recursively it will check that it contains still it is not nil, and finally when it will reach here, then it will this condition will get false, that x is not nil. X is nil now, that is beyond this there is no subtree or further leaf nodes are present, left tree or subtree. And in that case what will happen, in order walk tree will be get walking till it reaches to the last leaf node or the terminal node, and then it will print that value. So here we will get printed 12, and again it will walk to the right, in order tree walk to the right, and it will be printed. That means root node will be get printed here, and for the right node will be printed here as per the calling of this function in order tree walk right. And similarly for all the subtree, left, root and right will be get printed here. This is how we will complete the in order walk. Next is that in case of binary search tree, we have to consider the complexity also. What time it will take or how much space it will consider. While considering this binary search tree, how much space it will take or how much time it will take to perform its operation. This is the main important point here. In this case, all the dynamic set of search operations can be supported by the big O H time. This H represents here what is height of the tree, and when we will simplify this, we will get a height. This height is equal to theta of log n for a balanced binary search tree. This is to be observed here in case of binary search tree. And H is equal to theta of n. This is a case for unbalanced tree that resembles a linear chain of n nodes. That means we can say that it is a worst case here, because if you are considering a tree which is either left skewed or right skewed, it has to travel up to the last end, right, that is root node or terminal node. So that's why it will take theta of n, and in worst case it will take this much of time. Now another property of another operation of the binary search tree is searching element into the binary search tree, and this can be done in a two way with the help of tree search. That is, one algorithm is recursive, or one pseudocode is recursive, another pseudocode is iterative search. So what is the difference between those two, searching algorithm or searching pseudocode? In case of, we can see here that in case of recursive call, we have to check initially that x is equal to nil. If x is equal to nil or k is equal to key of x, then we have to return the x. Means in case of searching tree, there are two arguments, x and k. X is the tree, that is binary search tree, and k is the element that is to be searched here. If x is equal to nil, that means the element which is to be searched is the first element which is present there, and k is equal to key of x. We consider that key of x as a key, that is the root node, we can say here. It will return the value of that. But if this is not the case, if key is less than key of x, that is root node, we are comparing, because in case of binary search tree, we have seen the property that left node always will be less and right node will be always higher than the root node. So this property will help us to search while using the recursive call. And in this case, we will check that if the element that is to be searched is less than key of x, then what we will call here, we will search the tree left side of x. Means that element will be searched on the left search tree, and recursively it will be searched, because it is not necessary that the element is present on the left of the root node itself. It may be possible that the next level, the element can be present on the next level of the binary search tree. So that's why we need here to call recursively so that we can reach to the element till this condition satisfied. Means if the element is last element, then it will be very, as we can see here in example, previous example, suppose we want to search an element 12. What we'll do here, we will check this one, compare the this element with the root node. Since it is less, we will try to search on the left side of the tree or left side of the subtree. And again, when it comes to the root node, we will compare here. Again, it is less than the root node. Again, we will search the next subtree. This process will be continued till we reach the last label. And this label will be the terminal node if you are searching 12 as a element which is to be searched here. But if it is possible that in between any element is there, this will search and give you the result. And if it is not found in the left search tree, what we will do here, we will recursively search the right subtree. And in this case, the condition will be get changed here, because since we are considering here k as a smallest value as compared to the root node, if this is false, then the next condition will be the right subtree. That means it is higher than the root node, so it will be searched on the right subtree of the binary search tree. So this is what the recursively it is done here. And in case of iteration, what we are doing here, we are considering here a loop, two loop statements, while and do while. X is not nil, means we will go on continuing the searching process till it reaches to the last element here. In this case, it was just comparing and assigning the value that if it is not, then it will be the root node and we will get the result. But here in this case, if x is not nil and k is not equal to key of x, then what we have to do here is we have to check that k is less than key of x. If key is less than key of x, then what we have to do, you have to assign left x value to the x. And again, this process will be continued. That means continuously it will be compared with the key node or root node, we can say here. If this condition not satisfied, then it will go to the right subtree, which we have already discussed here, and then it will be get printed here. That means this loop will go on continuously, will be in the loop and give the result until this condition gets satisfied. As per definition of that is recursive and iterative, we can see here that iterative tree search is more efficient on the most computer, and the recursive tree search is more straightforward. That is, more straightforward means what? We can say here the system is being compared, and it has been said that in some case of computer, this iteration is very efficient, iteration method. But in some case, it is get complex, because as the data get increased, the complexity of this program also get increased. That's why it depends upon the system which algorithm or which pseudocode we are going to use here to verify that, or which algorithm we are going to find it out that what algorithm will work better. It depends upon the system. Now, another operation of the binary search tree is finding minimum and maximum. This is very important part, because when we are going to insert or delete some element into that, prior to that we have to find it out if that element which is to be inserted or deleted, we have to check it that it is minimum or maximum. By checking this, we can identify in which subtree the element will be get inserted here. This algorithm also helps in insertion and deletion also. And what this algorithm says here, or what pseudocode says here, that when we are trying to find the minimum and maximum, we know as per the property of binary search tree, this guarantees what? That minimum is always located in the leftmost node. This is the guarantee part of the binary search tree, and maximum is located on the rightmost of the node. So this simplifies our searching process here. So this is very important pseudocode which is to be remembered here. While finding the tree minimum, what we have to do here is we are iterating this algorithm or this pseudocode by a while and do loop. Simply we have to check the left of x is not nil. Means whatever root node is there, whatever tree is there, if left of x is not nil, that means some minimum value is present there. Else the root itself will be considered as a minimum value. Because we already know that property of the root tree is what? We have to, suppose this is 200, then this will be 150 and this will be 250. Means right side, whatever value is present on the right subtree will be higher than the root node, and left side will be comparatively lower than the root node. If this is not present here, that means root is the lowest value. This is what is signifies here. That's why left x is not nil. If this is true, then root itself will be the lowest value. And if this is false, then what we will do here, while left of x is not nil, we have to continue the statement till this is true, and we have to assign into x the left of the x, and then we have to return. That means we are just printing the left value of the given subtree, and left value of the given subtree will be the minimum. If there are subtree at lowest level, then we can easily identify what is the minimum value just by seeing the tree. If you want to do manually search, in that case, just by seeing the tree, we can identify by just finding out the leftmost element, that is left subtree. We can say that this is the minimum. And similarly, in the maximum case of maximum, what we have to do here is we have to check that right of x is not nil. Then only we can continue this searching operation, that is finding maximum into the tree, binary search tree, because maximum resides on the right side of the subtree. What we have to do here is we have to check this and assign the rightmost value of the x into the x and return the value x. This is very simple to remember these two algorithm, that is minimum and maximum. Now, predecessor and successor, another important part, because in order to know the predecessor and successor, this is very important. Successor is what? Whatever root node is there, that root node, the next element that is to be reached is as per binary search tree. If you are trying to search on the left subtree, the next subtree will be the successor. Next sub element or next root or next leaf node or terminal node will be the successor. Predecessor means whatever node is there, the upward, that means in upward direction we have to search the elements. Here, as per definition of successor of node x is a node y such that key y is the smallest key greater than key x. This is to be remembered here. Similarly, a very important point of predecessor and successor is, if you are considering the largest key, we are trying to find the successor of largest key, it will be always nil, because the largest value always reside on the right side of the subtree, that is tree or subtree we can say, and that will be the terminal node. And after terminal node, when we are traversing to the terminal node in the right of the subtree, we will get the largest value, and beyond that there is no any element. So this statement signifies here that this is a true, that successor of the largest key is always nil. Search consists of two cases. If node x has non-empty right subtree and x's successor is the minimum in the right subtree of x, and if node x has an empty right subtree, then as long as we move to the left of the tree, moved through the right children, we are visiting smaller keys. This is to be remembered here. Next is x successor y is the node that x is the predecessor of. That means x is the maximum in y's left subtree. X is the maximum in y's left subtree. Why? Because if we will see here example. In case of successor, if you are searching this successor of 213, because this is a rightmost element or rightmost leaf of the tree, and beyond that there is no any node, that means what? This is the highest value. That's why it is saying that there is no successor. for the rightmost element. And now we will understand what pseudocode for successor is. How we are going to identify what will be the successor. When we are trying to find the successor, we have to consider the tree, that is binary search tree, and priorly checking that right of x is not nil. This is the important condition that is to be checked here. If it is not nil, then what we have to do, we have to return the tree minimum, that is right of x. Tree minimum right of x. This is the successor. Tree minimum right of x. And we assign into y the px, the value that is to be searched. And next step is while y is not nil and x is equal to right y. Means whatever right of y is there, we assign into the x, and y is not nil. What we have to do here is we have to assign into the x y, and y is equal to p of y and return y. So there are two steps. First step is this one. We have to check that the tree is not nil. What we are doing, we are trying to find it out, the successor. Successor means what? If you want to find, if this is x, it's 56, and if we will compare here, right of x is not nil. As we can see here, the right of x is not nil. Then return tree minimum right of x. The tree minimum right of x means what? 190. Right of x, tree minimum of right of x. Tree minimum right of x. Again, it will move here, and this is a recursive call. It will continue till it reaches the value at the leaf or the last node, and this is how we can get the successor. Means successor of 56 will be 200, successor of this will be 190. This is what on the right side. Similarly on the left side, as per the pseudocode, next successor will be this one, next successor will be this one, and this is how we are going to get the successor. Now another code is binary search tree insertion. This is very important topic here, inserting element into the binary search tree. What we have to do here is change the dynamic set representation by binary search tree. Ensure the binary search tree property holds after change. This is very important part, because if the binary search tree property changes, that means that the tree, whatever tree is there, it will not be considered as a binary tree. And in that case, if the property of binary tree do not hold, that means it is not possible. Not possible to insert any element by simply inserting at anywhere, because it is changing the property of the binary search tree. This is a problem, or this is a important issue that is to be checked while inserting any element. Insertion is easier than deletion. Similarly, deletion, because again we have to maintain the property of the binary search tree. That's why it is important. And in the last in next session we will continue how insertion is done into the binary search tree and deletion. We will see with the example. And while analyzing all this insertion and we will do all this into the next video, tree deletion and deletion of zero. Okay, thank you so much. We will meet in the next lecture.